And um, in the today's talk, I will be discussing how can we secure cyber physical systems, while mainly focusing on what are digital twins, as per my understanding, and then how can we use digital twins to secure cyber physical systems, and as well as the security of digital twins themselves. And I will also talk a little bit about the industry projects in which I'm currently engaged in. Um, so, as we are all aware that usually the convergence of information technology and operational technology in cyber physical systems, it provides interconnected and autonomous operating systems. However, such integration also introduces cyber attacks, uh, and these attacks can have severe repercussions on the social, economic, and business sectors. So, under these circumstances, the question is how can we secure cyber physical systems? So, normally, the essential measures to secure cyber physical systems it involve evaluating the system functionality and security, but without affecting the ongoing or the live operations within the cyber physical systems. So, in this regard, we have various solutions, such as we can have cyber ranges or we can have intrusion detection systems. So, for instance, the intrusion detection systems they can uncover the malicious activities by identifying the deviations or the patterns from a defined benign behavior. However, here the issue is that the attackers may already harm the system infrastructure due to delayed countermeasures, as the mere detection of attacks by these solutions is sometimes of limited use. Other issues are the setup and the maintenance cost. It could be time and cost intensive. Most importantly, most of these solutions they do not provide a way to reproduce or reconfigure the scenarios for future investigation. And finally, they do not cover the entire life cycle of the product. So again, coming to the question that how can we secure cyber physical systems? So one of the promising solutions to secure cyber physical systems are digital twins. And digital twins, we can say them that they are the virtual digital replicas of their physical counterparts, where they should exhibit three key features. So, first, they must have sufficient fidelity in terms of attributes and services. Second, they must maintain a continuous synchronized feedback loop with their physical counterparts. And this continuous synchronization, maybe I will talk a little bit more about it in the upcoming slides. But for now, it could be either time or state dependent. And third, they must provide an objective, specific, actionable insights such as assessments, predictions, optimization, or any other capability related information while covering the entire system lifecycle. Now, there are a lot of other terms or concepts that are somehow used interchangeably with the digital twins. However, the concept of the digital twins is is actually a bit different than the rest of them. So, for instance, we can have digital models, which involves a manual flow of data or information, and they typically serve as a static or standalone representation of a physical asset. Similarly, in case of digital shadow, which introduces automatic but one-way data flow from the physical asset to its digital counterpart, and the digital twins, which I have already give you a context. In case of digital twins, it has to be an somehow semi-automatic or automatic data flow, considering whether there's a human in the loop or not. Now, in general, there are a lot of benefits of digital twins. originally the idea of digital twins, it started from NASA in 1960s, where they introduced the term of living models for one of their Apollo missions. I'm not going to go into the history, but the idea is that they called the not directly use this term digital twins, but rather they called it as a living model in response to one of their Apollo 13 oxygen tank explosion mission, where NASA used simulators and extended a physical model of the vehicle to include a digital component for the failure evaluation and recovery planning. So around in 2000s, then this term was basically coined as digital twins. Now, in the beginning, the digital twins, they are widely used in manufacturing context and in some industries related to aircrafts and so on. Uh, but then their application propagated to various other areas as well. So they have a lot of benefits ranging from production to system testing or resource optimization. So, for instance, in case of prediction, we can simulate various scenarios using either the real time or the historical data, or even sometimes synthetic data. They can help to forecast the potential disruptions. So, whether it's demand spikes or equipment failures or logistic bottlenecks, allowing businesses to proactively plan and respond. Now, moving forward, I would like to talk a little bit about the building blocks of digital twins. Here, the idea is we need to make sure that um, maybe some of these essential or desirable components we should have in order to create a digital twin. But of course, these are not all of the building blocks we need to create a digital twin. We also need some of the design or the operational or maintenance requirements. So I will start with the assets. We can have either a tangible asset or not tangible assets, which means we can create the digital twin of a product, or let's say a robotic arm. But at the same time, we can also create the digital twin of an event or a process or a system or even a service. Then the next important thing are basically the data and the data sources, because digital twins, they operate on data, and we can obtain the data as a historical data, or could be synthetic data, or even the real-time data from, let's say, the sensors or the actuators that are installed in any environment or in any facility. Um, then, of course, we need to store not only the physical data, but also the data from the digital twins. And depending on the resources or the requirements or the preferences, we can store this data on premises or by using any cloud-based solutions, or it could be a hybrid solution as well. Now, as every product or every system, they have their life cycle starting at the point of their design and engineering phase till the point that they are no longer operating or they become obsolete. So same is the case for the digital twins. So you design them, and then of course they operate, we need to maintain them, manage them, and finally if the product becomes obsolete, then in some cases the digital twins are no longer required. However, there are possibilities that we can archive the digital twins so that they could be used for other applications, or let's say for the next generation of those products. Next, we have this construction methodology, which I believe is one of the main component, and it is also known as the process knowledge. And I usually say it as one of the thinking capability we are providing to the digital twins. in addition, of course, to the data sources. So there are different construction methodologies, and in my opinion, they are usually connected with the simulation platforms. So, for instance, one of the simulation platform, which is named as Anylogic, and I'm currently working in it, it provided three types of construction methodologies, which includes agent-based, discrete events, and system dynamics. And each of them, they have a different capability. So for instance, the agent based, it can provide all of the units, or let's say the individual entities in any system. You can model them, but at the same time, the system dynamics provides a more kind of collective information about the system. And then in terms of digital twins, they can operate as a simulation mode or the replication mode. Here, the concept of the simulation, it could be mapped to the concepts which I mentioned earlier, like they could be the digital model or the digital shadow. Why? Because simulation, in case of simulation, it means that your digital twin is actually not directly connected to the physical system. Or in other words, we can say that the physical system and the twin system, they are not connected in real time. And in case of replication, it's more like, you can say, it's record and replay. So you record the information from the physical asset to the twin environment, and then you can replay it in order to know what is going on into the system and what type of, depending on the objective information or the insight, should be provided as a feedback loop back to the physical system. Then we can also focus on architecture. So for instance, whether we want to make the digital twin of the entire system, or we can consider some units or processes, or I also say it in a way that uh, before we start to make digital twin, we need to make sure that what is our objective of making digital twin. So based on objective, we can also decide that what are those critical assets in your system that you need to include in your twin environment. Uh,
Yeah.
original, Originally, the idea of digital twin is not to completely replicate the physical environment. Rather, we have to focus on only those.
Guys, could we please mute the mic?
Sorry, I just got a bit distracted. Uh, I was talking about the architecture of the digital twin. Depending on the objective, we can identify the critical assets, and then we can only include those critical assets in building the digital twin, rather than considering each and everything in the physical environment, which is maybe no longer required as a part of our objective. And then, of course, we need to have a proper user interface so that the analyst or the users or the engineers or any other end user can interact with the digital twin, either in terms of monitoring or queuing or obtaining any other information from it. Now, today specifically, I would like to focus on two aspects of digital twins. So as I mentioned that there are a lot of benefits, but in my research, I have mainly used digital twins to secure cyber physical systems. Um, and I will also discuss the security of digital twins themselves. So digital twins, they can be used for various purposes in terms of in the security context. So for instance, they can be used for intrusion detection, they could be used for cyber deception, digital forensics, incident response, testing and training platform, or even for threat intelligence. um, Now, here I would like to give an example from one of our works where we have used digital twins as a testing and training platform. So in this work, which we named as Enigma, which basically stands for securing digital twins through gamification approach, we use digital twins as a gamification platform by leveraging them as an offensive security tool to launch overt attacks on digital twins. Overall, the objectives of this research is first to provide security analysts with the training environment where the attack scenarios can be simulated in a controlled interactive setting so that we can enhance their readiness for the real world threats. The second purpose was to assess the security posture of the underlying system without, of course, negatively affecting the ongoing operations. How? Because all of the gamification or launching the attacks is actually done on the digital twin instances rather than the physical system. And lastly, we also evaluate the outcomes, the gaming outcomes through explainable AI in order to support justifiable reasoning on what, why, and how specific cybersecurity defenses are formulated in a gaming context. Now, if we zoom in here, uh, we can get to know a step-by-step approach for establishing this gamification platform. So for instance, we may start with the defining teams and their roles and responsibilities, and of course, the available resources. And then depending on the requirements and the gaming objectives, we can define a single or multi-stage simulated game scenarios as digital twins. And finally, we can also assess the gaming results. Uh, in this particular example, we have used a vehicle use case for our gamification scenario. And for the simulation tool, even though there are a lot of simulation tools available in the market, but based on our requirements, we have used Microsoft Azure Digital Twin. And in here we can start with the by in order to create a digital twin we can start by configuring the vehicle's electronic control unit or the ECU and establish a communication with the CAN bus, which is controller area network. So for the sake of simplicity, we just consider three sensors: speedometer, indicator, and coolant, which are installed at the respective ECU positions, and they emit the data to the vehicle's digital twin. Now, as part of Azure Digital Twin, the services or the configurations, these sensors, they are registered on Azure IoT Hub. And then there is an event grid which routes the sensor data by triggering an Azure function. And the idea of this Azure function is that it has to ingest, transform, and feed the data into the digital twin. And also this Azure function, it converts the data into JSON format in order to make it readable, and then of course updates the digital twin as it keeps on getting the real-time sensor data. And finally, as I mentioned, that we need to have an interface through which we can interact with the digital twin. Here, it can be provided with the Digital Twin Explorer. And if you're interested to get to know more about this paper, please feel free to access our paper and also the code. Um, I just want to add a couple of more points here. Here we have used Microsoft Azure Digital Twin, but as I mentioned, that there are a lot of other tools available. So we can have AWS, or we can also have other tools such as Mininet or Mini CPS. But all of these tools, they have their own pros and cons. So for instance, in case of Azure Digital Twin, it provides more like a kind of a graph, a type of digital twin without having any good visuals, let's say. So if the end users, they are not technically expert to interpret any information with the help of, let's say, with the help of the edges and the vertices and the connection between them, it might be a bit difficult to interpret the information. um, but on the other side, if I give the example of, let's say, analogic or some other tools, they provide a more kind of visually appealing information, and it's easier to interpret the information or to see how the physical environment in this virtual or digital environment. Now, I've also worked on the security of digital twins, and I came across this idea because digital twins, they are actually representing uh, a lot of information about their physical system. So if, let's say, we have a digital twin of a nuclear reactor, or even some of the cities or even the countries, they have made the digital twin of their cities or maybe any other critical infrastructures. So the point was that if the attacker gains access to the digital twin rather than the physical environment or the physical infrastructure, so there are possibilities that they are able to infer the information or the process knowledge which is embedded in the digital twin from the physical environment. So here I would like to discuss three abuse cases. So the first one is garbage in and garbage out problem. Now, the problem is that the digital one of the major risks to the digital twins is could be in terms of data integrity, as they heavily rely on the inputs, uh, 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 because they heavily rely on the accurate inputs, uh, and also they are a sort of central hub for acquiring and disseminating data from various sources, including the physical assets or the knowledge bases, which could be the historical data or maybe other reference digital twins. So as digital twins, they evolve over their life cycle, let's say starting from the design to the operation phase to the end of life, they rely on the data to evolve their capabilities and, of course, optimize the underlying system services or capabilities. However, here the digital thread, which actually can connect multiple digital twin instances or even um, different life cycles in the system, they could be vulnerable to manipulation. So any data adulteration along this thread, it could lead to garbage in, garbage out problem, where the digital model no longer accurately reflects the physical system behavior, reducing its utility and potentially compromising the system performance. And other abuse case is basically related to the risk of information leakage. Here, there is a concept which is named as fidelity. Now, fidelity means what is the degree of resemblance between the physical system and its digital counterpart. But fidelity, it actually depends on other factors as well. So, for instance, the synchronization between the physical system and its virtual counterpart. No, as I mentioned when I was like in the beginning, I was telling about digital twins. So I mentioned that there has to be a continuous synchronization. And this synchronization, it could be time or state dependent. No, here it means that if this synchronization is happening with extreme frequency, like with higher frequency, then there are possibilities that this information leakage, it becomes more problematic. And then another thing that depends on fidelity is contextual abstraction and, of course, resource consideration, such as computational needs, and, of course, the underlying objectives. So at one end, the high fidelity digital twins, they are essential for accurate replication. So, for instance, if I'm using digital twins as a cyber deception platform, it means that the underlying system or the underlying digital twin system, it must be presented in a way that it keeps the attacker engaged. But on the other end, if let's say the attacker, or with the help of any insider, they get to know or they get access to the digital twin, so in that case it becomes, as I mentioned, more problematic. So this paradox actually becomes a digital twin trilemma, where we need to have a balance between representation, which is uh, mm, what to what extent we should be, providing or representing the information in the digital twin, and then security, and the third factor is basically fidelity. Now, beyond isolated threats, digital twins, they also face the risk of cascading inconsistencies or failures, particularly in case of hybrid attacks. Now, by hybrid attack, I mean to say that there are possibilities that the attacker, they can reside at the physical system, but also as at the twin environment. And even though there are no such attacks where the attacker are able to access the digital twin, but of course there are attacks, a lot of attacks, where the attackers are able to attack on the cyber physical system. Um, but just imagine that, like in this hybrid attack figure, if the attacker is able to gain access to the virtual environment or the twin environment, which are represented as green circles, and as well as the physical environment, which are represented as the blue circles, then the this is one of the representation that how the attacks can be propagated from either the physical system or the twin environment. And it becomes more problematic in a way that the digital twins, they might be having this continuous synchronization with their physical counterparts. Now, some of the countermeasures which I would like to share, but again, at a quite an broader level, are uh, first thing that could be done is to design a variable fidelity digital twin so that it can strike a balance between generalization and contextualization, and there we can have sufficient fidelity to minimize the information leakage while at the same time meeting the objectives of using the digital twins. The second could be to design resilient and context aware digital twins so that if there is a system under attack, so the system should vent into a fail-safe state. So with fault-tolerant support, digital twins must localize the compromised component and then allow the system to fail over to either a replica or a default state, enabling the restoration of the system state through digital twin. Maybe we can have different versions of digital twins. And lastly, we can implement a mechanism to validate all the inputs or the outputs within the digital twins in order to ensure transparency and accuracy as the part of their operational life cycle. Um, Now, lastly, I would like to discuss some of the projects in which I was involved and I'm currently working on. So the first project, it was already completed, but the idea in this project was using digital twins as an incident response. And here we proposed a framework which can serve as a guide for the plant operators working in a manufacturing industry in order to guide them on how to design, develop, deploy, and manage security enhancing digital twins based incident response solutions across different phases. And here we selected the starting from the prerequisite phase to design and engineering phase, and then operation and maintenance, and finally the end of life. Um, Here, we use, in order to evaluate this proposed framework, we use automotive manufacturing industry as the underlying use case, where we discussed the application for the entire incident response lifecycle. And additionally, we also compare and map the framework against some of the state of the art academic research papers and also the industrial solutions, such as the one provided by the Digital Twin Consortium, and they named it as the periodic table, capabilities periodic table, in order to identify the gaps between the academia and the industry practices. And at the moment, I'm involved in another interdisciplinary UKRI funded project, which is named as RISK, Reimagining Supply Chain Network Plus. And in this uh, project, I'm responsible for building the digital twins for the supply chain, and also to conduct the threat modeling of not just the cyber physical environments that are involved in different supply chain stages, but also the threat modeling of digital twins themselves. It's quite a big project, and here we have to work on three different use cases, starting from food, fashion, and critical minerals. And at the moment, I just started working with one of the food company in Ireland, and we have to develop a digital twin of their glass house or the greenhouse. Um, I also want to just bring your attention to another call. Maybe I can share the link later with you. So there is a kind of a networking platform within the UK. It is named as Sprite Plus Hub. And they recently initiated a collaboration with one of the cybersecurity lab in UNSW, the university in Australia. And the idea is to come up with any theme that is related to trust, security, privacy in any domain. So I also started working with that cybersecurity group. Um, Again, with the idea of the food supply chain within UK and as well as in the Australia. So I believe that maybe there could be some opportunities for the future collaboration with our MIT as well. Now, these are some of the references, and thank you so much for having me, and thank you so much for your attention. If you are interested in research collaboration, so please feel free to drop me an email, and I look forward to any questions you may have.
Thank you very much, Sabah. Very interesting work indeed, and very insightful talk. Yeah, we have still time for questions. So any questions, you're welcome.
I don't have questions. Just to say something, Sabah, it was really excellent. Well, we have a big project here, similar in Melbourne, with the research hub on digital manufacturing. We're building a digital manufacturing twin, and with all the security. So it'll be great to talk to you. I mean, not now, but later on. That was funded by the government up to $5 million, plus the company's 7 million. We're working between Swinburne, Sydney University, and UQ, University of Queensland, with Helen, and with the people from, I don't remember as well. So it'll be good to chat a little bit. I mean, because I'm interested. You have some case studies, right, in manufacturing as well, right?
Yeah.
What is the scale? Which manufacturing processes did you use? Did you test it in real time? Your digital twin?
No, for that DT Cyber project, because it was a short project, and I joined
Right.
like in the last, like, let's say 8 months, but it was more like a theoretical framework, I should say.
Right.
Yeah, but I have worked like quite a lot on manufacturing industries. Unfortunately, not with any industry so far. So I would be really much interested to, get to know.
Right.
Maybe some other time we can
Yeah.
discuss. Yeah.
We will chat. We'll chat also.
Yeah.
Yeah. We'll chat. Yeah. And did you do it also in the supply chain as well? Did you a case
Yeah.
study? Did you in which area?
Yeah, and
Supply
at the
chain.
yeah, in supply chain at the moment, we started working on food supply chain, where we have a strawberry company, and they want
Right.
us to make the digital twin of their greenhouse. So as a starting point, we just have the food supply chain, but
Right.
the other use cases could be like fashion and clothing and the
Right.
critical minerals. Yeah.
And how long it takes you to do the digital twin of, for example, of what a certain case? Well, how long in your case, for example?
I mean, as for this Risk Plus project, we are still in the hiring process, but
Right.
yeah, I have started working and using Analogic, so maybe I believe it's quite an interesting tool, and for a
Mm.
very basic simple idea, it might take you uh, let's say 10 to 15 days, uh, just to come
Okay.
up with a very simple,
Basic.
idea. Yeah, yeah,
Yes. Okay. Okay. We'll probably talk to you because
yeah,
we need some feedback from you guys. Okay. We'll talk to you. No problem. Thank
yeah,
you.
yeah,
Thank you,
yeah,
Sabah.
sure, sure. Thank you, Suhail.
Thank you.
Any other question from the audience? Yeah, looks like you've explained it so well, Sabah. There are not many questions. So if no more questions, I think we can finish it here, so that you can still catch up on your sleep. It's still midnight at your end. Yeah, I'd like to take this opportunity to thank you again. It was a great talk. Yeah.
Thank you so
Great job.
much.
Well done.
Yeah,
Well done, Sabah. Well done.
thank you.
We keep in touch. We keep
Yeah,
in
yeah,
touch. See
sure,
you.
sure,
Bye-bye.
sure. Yeah,
Thank you, everybody. Thank you. Bye.
thank you. Thank you. Bye. Bye.